Okay, well, welcome everybody to tonight's MyMoon and MyMoon Hangout with our partner CosmoQuest. My name is Andy Shaner. I'm at the Lunar and Planetary Institute in Houston. And with us tonight is Dr. Catherine Neish from NASA's Goddard Space Flight Center. Um, Catherine is a postdoc at Goddard, and she's a member of the LRO Mini RF team, which is Mini Radio Frequency, which is a
That's right.
radar on LRO, and she's also an associate member of the Cassini radar team. So we're gonna chat with her tonight, talk about what all that means, and what she does there at Goddard. So, Catherine, why don't you just start off just telling us what do you do at Goddard?
That's a good question. No. So I am, as you mentioned, Andy, a member of the Mini RF team on the Lunar Reconnaissance Orbiter. So this is just one of 7 instruments on board LRO, and this spacecraft was launched in 2009 to increase understanding of the moon for a few reasons. Mainly at the time, NASA was very interested in sending humans back to the moon for exploration purposes. So this was a partnership between the exploration side of NASA and the science part of NASA. And we've just learned so much about the moon with this new spacecraft and several other international spacecraft that have gone up around the moon. It's really been, ushered in a renaissance in lunar science. And one of the main focuses of LRO was to look for resources for astronauts, one of the most important being ice, for example. So I'm not sure if you guys have heard, but very recently the Messenger spacecraft around Mercury confirmed that there's large deposits of water ice near the poles of Mercury, which seems kind of crazy, given that Mercury is the hottest planet in the solar system. But it turns out Mercury, just like the moon, has these places called permanently shadowed regions near the poles where it gets cold enough to trap volatiles like water ice and other things that are normally in a vapor phase on these planets. So one of the main points of LRO was to look at the poles to determine if there's water there and how much there might be. And the way we help with Mini RF is it turns out that large deposits of water ice have very unusual radar signatures. So we're basically taking a big radar flashlight and pointing it at the poles of the moon to see if there's any bright radar return there that might be indicative of ice. So that's one of the things I do. And there are plenty of other instruments on board LRO that were also put there to help us understand whether or not there's ice there. And of course, we all talk to the other teams and try to come up with sort of a whole picture about the moon and what's going on there. So that's what I do in a nutshell.
Okay, great, thank you. If those of us, or I'm sorry, those of you that may have just jumped on recently during the middle of Catherine's talk, little bit there, we're talking with Dr. Catherine Neish from the NASA Goddard Space Flight Center. She's on the Mini RF team, instrument team on the Lunar Reconnaissance Orbiter. And I just want to remind everybody that if you have any questions for Catherine, you can put that either on the event page for this Hangout on YouTube if you're watching it on YouTube, or via the Twitter hashtag MyMoonLPI, all one word, and you can see it there under my name there in the lower third. So yeah, Catherine, that's a great point you brought up about LRO. That it was really this cross between bringing science and exploration together, and in fact, that's I think that's its mission's motto or something. It's on like the logo, I think, for LRO, but it's like in Latin.
Possibly. I don't know.
Yeah.
Yeah.
So have you obviously you're doing some of the science for us. Have you done anything in terms of the exploration? I mean,
Right.
like you said, they're together, which so it's kind of hard
Yeah,
to separate
yeah.
them.
They are very complementary. So one thing that NASA was very interested during the exploration phase of the mission was to look for certain landing sites. They were called constellation regions of interest because at the time the program to go back to the moon was called Constellation. So a group of scientists got together and chose 50 different sites on the moon. Their top 25 and their bottom 25, so tier 1 and tier 2. And so one of the things LRO focused on specifically in the early part of its mission was to look at these 50 sites to determine both their interest to scientists, but also their any landing hazards you might find, resources in that area. So one of the things I've done is to take a really close look at those areas in radar. In addition to being very good at finding deposits of water ice, radar is very, very sensitive to rocks. Rocks of about centimeters to maybe about as big as a meter. So this would have been great for Neil Armstrong back in Apollo 11 to know, where to put his spacecraft down. And actually, he had to do this on the fly when he noticed there was this huge boulder field that he was originally intended to land in, and he knew that he had to fly over that and touch down somewhere safer. So now with LRO, we can determine where those safe landing spots are in advance. So that's one of the things we can do with radar, as well as some of the other instruments on LRO. There's also a very high resolution camera called the LRO camera, or LROC, and they're able to see things as small as a meter in size. So a combination of these instruments can help us find safe landing sites for future manned trips to the moon.
Excellent. So the mini RF, the radar could. So if I'm hearing you right, the resolution limit of LROC is about a meter. Anything maybe smaller than that is a little iffy. So we could use mini RF to, I guess maybe
Right.
I'm not sure what I'm looking for, but
yeah, smaller rocks.
Right. Yeah.
Exactly.
I see here. I was trying to use like some fancy word and I just couldn't think of it.
Right.
But yeah, smaller rocks. Okay, excellent. So Paul Spudis, I believe, is the PI.
He was the PI of the instrument on Chandrayaan-1,
Okay.
which was the Indian partner. That spacecraft unfortunately died in 2009. The PI of Mini RF is Ben Bussey, who's at the Applied Physics Lab
That's right.
in Columbia, Maryland.
Okay. So you bring that up. What's both Mini RF and Mini SAR are radar?
Yeah.
But what's the difference between them?
So Mini SAR, which was the instrument on Chandrayaan-1, was meant to be sort of a test run for Mini RF, so it was a little bit simpler. Actually, we also called it Forerunner because it was the forerunner to Mini RF. So it only had one wavelength at one resolution, and the resolution was rather low. It was 150 meters. With Mini RF, we had two wavelengths, 12 centimeters and 4 centimeters, and we had two resolutions, the 150 meter resolution, but also we had a zoom mode which showed us features as small as 15 meters. And that really has helped us understand the moon a lot better. You get that tenfold increase in resolution, and suddenly you can see features that weren't visible before. So most of the data we got with Mini RF are at that 15 meter resolution.
Great, very good. And I want to ask one more question, and then we'll see maybe if there's anything over in our view. Any of our viewers have a question. But when a lot of things first started coming out, a lot of the data started coming out, I heard this term called circular polarization ratio.
Yeah.
Now, I have no idea what that means, and I have tried to understand that. Is it really that complicated, or is there a really simple way to explain what this is?
Very simple. It's very simple. Unfortunately, it has the acronym CPR, so it sounds like you're doing emergency medical, assistance with somebody. But all it is a ratio. So just like the simple math you learned in grade school, where you take one number, you divide it by another number. So CPR, you take one type of radar with one polarization, and you divide it by another type of radar with the opposite polarization. So electromagnetic waves have a certain polarization. In radar, we like to talk about circular polarization. So you can imagine a wave going through space like a circle. So that would be one polarization. If you go the other way, that would be the opposite polarization. So what we're measuring is just the ratio of those two things. And it turns out that ratio, just those two polarizations, can tell you an awful lot both about the presence of ice on the moon, but also the roughness, those rocks I was talking about earlier. And and it has to do with how electromagnetic waves interact with surfaces. It turns out that when you bounce a wave off a surface, it will go from this direction to this direction. Oops, I can't see that. The opposite direction. And that tells you something about the surface. If the polarization doesn't change, that tells you either it bounced twice, and so you probably have a lot of really big blocks on the surface that would cause it to bounce twice, or it never bounced at all and it just went through ice. So that's why we use these ratios to tell us something about the geology on the moon.
So just real quick, where you said how if it looks like it bounced twice, that means there was it's like a big boulder. Is this? Do you know this because of doing similar things on the Earth?
Yeah.
Okay.
Yeah, actually, there's a great analog on the Earth. It's called SP Flow. It's in northern Arizona. If anybody's going up to the Grand Canyon, you can make a bit of a detour and see this wonderful lava flow that's basically made up of radar-sized blocks. So just imagine, 20-centimeter-sized blocks all stacked on top of each other that made up this lava flow. So what you're getting is a bunch of corner reflectors. So you get the radar bouncing off. Hang on, let me see if I can get twice off the blocks, and so it's called double bounce backscatter. And this lava flow in northern Arizona has enormous circular polarization ratios, but there's no ice there. So clearly, there's more than one way to cause these high ratios. So we use terrestrial analogs all the time to help us understand what's going on the moon. It's been very helpful.
Oh, I bet. Yeah, I've sat on that lava flow. It hurts.
Yeah.
So we have a couple of questions from our viewers. Michael asks, can radar detect live meteor strikes? And if so, was there any detected?
I think they use that in the Earth's atmosphere to look for meteors striking the Earth. I don't know too much about that, but that you can see in the terrestrial atmosphere. In terms of the moon, I don't think you'd be able to use radar to see that. They're so infrequent. It's very unlikely. I think we won't be able to see that at all. Although we do have some folks looking for new impact craters on the moon. So they're taking pictures that we took in the 70s with Apollo and comparing them to brand new images that were just taken by LRO. So you've got a time span of about 30 years there. And you can find new impact craters that weren't there 30 years ago, but are there today. And so that's one way we can, not radar, but the LRO spacecraft can help us to understand how many objects are striking the moon in the present day.
Cool. Another question from Eve. So I think this is in reference to CPR. So it is kind of like dual polarization. So is it kind of like dual polarization in weather or Doppler radar? Meteorologists use this to determine types of reflectors, that is rain, droplets versus ice crystals or hail, etc. Is this a similar idea?
Possibly. I don't know a lot about weather radar, but the principles are the same. You're taking a signal and you're bouncing it off raindrops or hail or whatnot and receiving a signal. But I guess I don't know enough about the different signatures from rain versus hail to say if it's the same thing, but it certainly seems plausible. Terrestrial radars like weather radars or radars that track airplanes, very similar concepts. The only difference really is the scale involved. With terrestrial radars, you're only going out, hundreds of miles at most, whereas with planetary radars, you have to be able to span, astronomical units in some cases. So you need really, really powerful radars. That's the big difference. But in general, they're very similar in concept.
Yeah, see, and you did some of that work with bouncing radars across distances of astronomical units when you were you were an intern at Arecibo?
Right, yeah.
For a summer?
Yes. I worked at Arecibo telescope, largest radio telescope in the world down there in Puerto Rico, and they've used that to to look at objects as far away as Saturn and its moons. So that's 8 astronomical units away. So these radars are very powerful and can see very large distances. With LRO, you're only, say, 50 kilometers above the surface. It seems easy by comparison.
Right. Okay. Well, thank you for your questions, Michael and Eve. Hopefully, we'll get some more here in a little bit, unless maybe we have some now. So you study impact cratering. I don't know specifically what you have. That seems to have been kind of a focus. So are there any, or maybe the question is, what are the advantages to using radar to study impact cratering versus visual imagery or even topography data?
Right. Well, radar has a big advantage in that it can see below the surface. Not very far. At the wavelengths we're talking about, you can see maybe a meter or two below the lunar surface. So this allows us to see blocks and features that you can't see with optical imagery, because with optical imagery, all you're detecting is the very top, micron or nanometer of the surface. And with radar, you're probing underneath all that dusty regolith on the top of the surface to see blocks or melt that's formed in impact craters. So one of the things in particular that I've been doing is using radar to detect new impact melt flows on the moon, which might be buried over time. So impact melt is something that's commonly formed in impact cratering events when the projectile hits the surface, generates very high pressures and temperatures, and the substrate melts, and it turns into essentially a short-lived lava flow that can then spill out over the sides of the crater and produce these melt flows. But they degrade pretty quickly over time, so you might not be able to see them with optical imagery, but with radar, where you can probe beneath the surface, you can detect them very easily. So that's one of the things, one advantage radar has over optical in studying impact craters.
Okay, that's a good advantage to have. And Nick asked a question: which has more ice now? Not sure what he means by now, but which has more ice now, the north or south of the moon?
We don't know the answer to that question. I could make some guesses, but from the data we have now, it's not entirely clear. So unlike Mercury, the moon isn't quite as bright in radar, but there are a few interesting craters near the north and south poles that do have this intriguing radar signature that might have ice in them. So if we're basing it on that measure alone, I would say there's probably more unusual craters near the north pole of the moon. Unfortunately, the LCROSS spacecraft, which is the only spacecraft to directly detect water ice on the moon by impacting it, this happened in October of 2009. It was aimed towards the South Pole. So we have a very good idea of one place on the South Pole and how much water ice is there, and it looks like there's about 5 to 8%. But there hasn't been a comparable mission to the North Pole of the moon. And again, that's just one spot on the South Pole. So I'd say right now it's hard to tell. But if I had to guess, I'd probably go looking at the North Pole. There seem to be a lot more promising candidates up there.
And what do you mean when you say the moon's not as radar bright?
So ice has a very bright radar signature. And you see this on Mercury very, very plainly. There are craters there that are in constant permanent shadow, which are very bright in radar return. And MESSENGER has confirmed that these craters are in fact filled with water ice. There is evidence from a neutron spectrometer that this is consistent with water ice. Neutron spectrometers are detecting the amount of neutrons coming off the surface of a planet, and since hydrogen has the same mass as neutrons, where you have hydrogen, you have less neutrons. Because just like billiard balls, when they hit each other, that neutron's going to lose all its energy when it runs into a hydrogen. So we see both this bright radar signature, but also this very low neutron count which tells us there's definitely water ice in those craters on Mercury. On the Moon, you also see that low neutron count, but the resolution of the instruments isn't perhaps as good enough to pinpoint the individual craters near the poles of the Moon. So this is where you'd want the radar to help you sort of get that higher resolution imagery. Unfortunately, the craters on the Moon do not seem as bright as they do on Mercury, which either means that there isn't as much ice there, or it's broken up into little chunks, or it's buried so deeply that we can't see it. Although, if that was the case, we wouldn't be able to see it with the neutron spectrometer either. So I think what's happening is that there just isn't as much ice near the poles of the Moon, and what ice is there is broken up into little pieces that wouldn't be bright to radar like they are on Mercury.
So when you say something is radar bright, does that mean like it looks bright?
Yeah,
like there's a lot of light
bright.
coming from it?
Well, it's your own reflected light. So you take your radar flashlight and you shine it at these craters, and what you're getting is just that light reflected straight back at you. So that's what you're seeing.
Okay, but it's not bright like visual light. It's bright in radar,
yeah.
which is radio waves.
Right. Yeah.
Because if you're looking at a permanently shadowed area of the Moon, you're not going to see any light.
No, yeah, it's going to be very dark. That's right. Dark optically, bright in radar.
Right. Okay.
So, because radars, like I said, they're flashlights. You're bringing your own power source, whereas optical imagery, you're relying on the sun to see inside those craters. And since the sun never shines in those craters, you don't see the craters in visible light.
Right.
You need a really big flashlight to see inside those craters.
Like the sun, but it just doesn't work.
In a different place.
Right.
You could move the sun to a different place in the sky.
Okay, I think we'll get a couple of more, or at least one more here. What transmitting power do you need for having good signal to noise with these bodies like Moon, Mercury, Venus, or Titan?
I think it's like a megawatt. I could be wrong about that. Yeah, something like a megawatt. I'd have to double check, but that's what's coming to mind straight away. Yeah. So we do sometimes have problems with Arecibo where the transmitter fails, and then you're not able to see anything really. But when it's working, you've got quite a powerful radar there. They actually shut down the road that circles the telescope. So it's about 1 kilometer around, or 300 meters across. And when the radar's on, they actually there's some lights that are flashing at the observatory, telling people not to go down there. Because oftentimes people will go down there to go jogging or to take a walk. But they don't want you to be microwaved. so when the radar is operating, they advise that you not go down there.
Wow. All right, well, thank you for that. From Sylvan, looks like maybe they jumped over from Learning Space to come to our Hangout. So thank you for doing that. That's great. I don't know, maybe it's just me. Maybe you know this. Know better about this, but it seems like maybe it appears as though the use of radar on spacecraft maybe is becoming more popular, or has it always been there and has just kind of been lost in the background to like the visual imagery and spectroscopic data?
No, actually radars have been relatively rare, and I think the reason for that is they were quite big and heavy and consumed a lot of power. And so if you have a spacecraft and you want to get as much data from it as you can, you're going to take the small, light, instruments that don't require as much power. So back in the 90s, one of the big missions then was Magellan, which was a radar mission to Venus. And there it made perfect sense to have a radar because you can't see through the clouds of Venus with optical imagery. But the whole spacecraft was a radar. It was big and heavy and used up a lot of power. What I think we're seeing now is that radars have improved to the point where you don't need the entire spacecraft to be a radar. Mini-RF is just one small instrument on LRO, and there are 6 other instruments on board. So you're not consuming your entire spacecraft with just one instrument. So I think just the technology advances has led to a bit of a renaissance in radar technology, because we use them all the time on the Earth. There's some very sophisticated radars that are currently orbiting the Earth. The Earth is, in fact, the best studied planet in radar. And so now I think people are looking at applying these technologies to other planets.
Cool, very cool. And going back to the water, the ice on the moon, because I've heard Paul Spudis has talked about there's 3 different flavors of water, or ice on the moon, and I think it has something to do with maybe how much water, or like if it's like sheets of ice versus little bits of water is kind of mixed in with the regolith, or if it's just like a little very light frosting kind of coating.
Yeah, yeah.
Can you, obviously I'm guessing you can tell that from its radar signature?
Right, so there's only one of those 3 flavors can you actually see with radar, and that's the thick deposits. It has to be about a meter or so thick. So I like to call that the skating rink type of ice. You need a thick pile of it in order to see with radar. If it's small chunks or just a frosting, you're not going to see that with radar. You need other instruments to see that.
So where are they coming up with these 3 flavors? How are they getting that data?
So I think what he's talking about there is there was some discoveries a few years ago that there is this OH layer kind of covering the entire moon that is not very thick, and you need an awful lot of it to make a cup of water for yourself to drink. So that's not a very useful resource for manned exploration. Then there's the sort of water that L-Cross found when it impacted the south pole of the moon, which we can't see with radar, so we know it's not this thick skating rink deposit of ice. It's probably just small chunks or crystals of ice mixed in with the regolith. So that's a better resource for humans, but it's not as much as the thick deposits like we see on Mercury. And what he's talking about is there are some craters near the poles that look like they might have the radar signature you'd expect for ice, but it's not as clear as it is on Mercury, because as I mentioned earlier, there are other processes that can create this radar signature, the sort of like the SP flow sort of idea. And so we're still actually we're undertaking some experiments using Mini-RF to try to tell the difference between ice and just blocky craters. So I'm really looking forward to see the results from those experiments.
Cool. Nick asks, are any future missions going to be carrying radar? So, for example, LADEE is the next lunar mission that launches this year.
None of the U.S. missions currently planned have radars, but there is a European mission going to the Jupiter system called JUICE, which will be carrying an ice-penetrating radar. So this is longer wavelengths than what we have with Mini-RF, but it should be able to see beneath the ice on Jupiter's moons Europa and Ganymede to try to see if there are any subsurface layers of water there, which might be good places for life. I'm hopeful that radars will be included in future missions that have yet to be planned. I would love to see a radar go to Mars, for instance. It seems amazing, given all the spacecraft we sent to Mars, that none of them have had an imaging radar on board. There are 2 penetrating radars called MARSES and SHARAD, which are more like the ice-penetrating radar I was talking about earlier, and those have done some wonderful work understanding the ice deposits near the poles of Mars. But I'd love to see somebody send an imaging radar to Mars as well, so we can compare Mars to the other planets where we have radar, like Earth, Venus, the Moon, and so forth.
And what specifically would you hope to learn by that comparison?
Well, there's a few great things you could do with a radar on Mars. First of all, Mars is covered in dust, sand and dust, which tends to obscure a lot of finer details. But like I said earlier, radar can penetrate beneath that dust to see features below it. And so on Mars, you might have ancient stream valleys that are currently covered in dust and sand that you can't see in the optical imagery that we already have. But if you send a radar there, you'd be able to pick them out really easily. And we actually do this on Earth in the Sahara Desert. You can see streams that you wouldn't be able to see with optical imagery alone. Also, we've been talking a lot about ice and water. And actually, water is very, very bright in radar. So you might be able to find some of these temporal streams that we think might be occurring on Mars today, coming out of crater walls and so forth. Those would show up really brightly with radar. So there's a couple of different areas, I think, that would benefit from understanding on Mars using an imaging radar.
Oh, very cool. Very cool. Another thing that's come across here is, can you compare radar to laser altimetry?
Well, they're similar, actually, techniques. With radar, we have our 12-centimeter flashlight. With laser altimetry, typically you have a 1-micron flashlight. And they have different sort of purposes. Typically, the laser altimeter is used to look at topography of the surface. And so LOLA is an instrument on board LRO, the Lunar Orbiter Laser Altimeter. And we've gotten amazing topography from that instrument. And that's really helped us in our understanding of lunar geology. So you can do things like take the topography from LOLA and compare it to the radar signature we're getting from MiniRF and understand things about impact craters or mountains or whatnot on the moon. So they're similar techniques, very complementary, and so yes, we do a lot of work comparing radar to laser altimetry data.
Okay. So Catherine did her PhD at the University of Arizona, which actually is where I first met her when I was there also. And at U of A, you studied aqueous organic chemistry on Titan.
Yeah.
And now you have now you have a bachelor's in physics and astronomy. How do you go from that to studying aqueous organic chemistry? How do you make that leap?
You know, I think I've just been a very curious person, and I love interdisciplinary science. I love to see the connections between the different sciences. I think that's where all the exciting work really comes from. So as an undergraduate, you know, I saw that I was interested in planetary science, and I saw that I was interested in understanding how chemistry related to geology, related to astronomy, and so forth. And so I think that's where the leap came from, and just my interest in understanding the gaps between the sciences. So I have a very broad interest. I like to call myself a fake chemist and a fake geologist. I don't feel like I'm necessarily an expert in anything, but you know, I think there's room for people like me in science.
Well, planetary science in itself is a very interdisciplinary
Exactly.
field.
Yeah.
So it's not surprising. Did you have to take a lot of chemistry when you got to grad school? Or
Well,
did
you
you
know,
have...
it's amazing. I did take a few courses, but you realize how similar the different sciences are. For example, I took a physical chemistry course in graduate school, and I realized it was just the same as the thermodynamics course I'd taken as an undergraduate. It's just pitched a slightly different way. So the sciences aren't so different as you think when you start, you know, studying them in more detail. There's a lot of overlap. It's just a different way of describing the same process.
Interesting. Very interesting. So like I said, you do radar studies with the moon and with Titan. When you get some new radar data back, what is the first thing that you look for in that data?
So, well, I guess Titan is a good example. Titan is Saturn's largest moon, and has a very thick atmosphere like Venus. So for a long time, we had no idea what was on its surface. And then Cassini arrived in 2004, and was able to use the radar on board to see what the surface looked like. And so back then, every radar strip we got in was just new discovery after new discovery. And this is sort of my favorite thing about planetary science, and especially working on missions. It's just you get to be an explorer in a way that I think we don't see as much on Earth. Back in the days when people were sailing around the world, discovering new lands and new species and whatnot. We get to do that as planetary scientists to this day. I mean, there's still places on Titan that we've never seen before. And so every time we get a new radar strip from Titan, I just want to see what new and fascinating things we might find. Because Titan really surprised us. There were a lot of features there we weren't expecting to see. Before Cassini, we thought maybe Titan had a large global ocean just covering the entire moon. And then instead we found seas of sand dunes around the equator, and streams and small lakes near the poles. So it really surprised us, and so I love the discovery aspect of planetary science, and that's, I don't know, that's what I do when I find a new radar strip.
Okay. Anybody out there viewing out there in the intranets? Anybody out there have any questions or comments? Remember, you can do that if you're watching on. You can do it through YouTube. You can do it on our event page on Google Plus, or you can do it through MyMoon, or I'm sorry, through Twitter using the hashtag MyMoonLPI. So there's something from Nick saying we get our own frontier era. That's true.
Exactly. Yeah, I TA'd a course at the University of Arizona called The Golden Age of Planetary Exploration. Oh. And people kept asking me, well, what is the Golden Age of Planetary Exploration? And I think it's right now. I mean, the last 10 years have seen so many missions flying to so many different places, so many great discoveries, from Mercury all the way out to, in a few years, Pluto. It's just been an amazing time to be a planetary scientist. I feel really lucky to be involved in these missions.
Yeah, it's New Horizons. Does New Horizons have a radar on it, or is it just a visual? No, there's
cameras and whatnot, but no radar. I was really saddened that Messenger didn't have a radar either. I would have loved to see Mercury in radar, but they did an amazing job packing as many instruments on board that spacecraft as they could for a $500 million budget.
Right.
So, props to the Messenger team.
Exactly. Yes. So I read that you were inspired by the Carl Sagan's novel Contact.
Yeah, a little bit of a geek there.
No, that's okay. How so? What about the novel inspired you?
It's a good question. I think in some ways I saw myself in the main character, and as a 16-year-old girl, there weren't a lot of role models to look up to at the time, and so I saw that she was doing exciting science and traveling the world, and I thought that sounded amazing, and I wanted to do those things. It seemed real, I guess. A lot of science fiction seems way out there, like it would never happen. You can't relate to it. But I felt like Contact was relatable. It was in the present day, with real people doing real science. It seemed like it could possibly happen. So I think that's what really attracted me to Contact, and was probably the reason I applied for the internship at Arecibo, since Arecibo plays a large role in that book. So it kind of had a pretty important role in my career, since Arecibo is where I got introduced to radar, and the rest has sort of been history. So thanks to Carl Sagan for inspiring me to be a radar scientist.
Well, the thing about Carl is, I'm sure he has inspired quite a few people. Another question from our viewers, from Keith: what is the diameter of the radar beam when aimed at Titan?
Oh, I'd have to do some calculations for that. It's going to be a lot bigger than Titan, I guess, is the main point. And so, you're getting all of Titan in a big radar beam. The only planet where you can really focus in on smaller regions is the moon, actually, from the Earth. Most of the time, you can only see, say, one hemisphere, or you're just consuming the whole planet. So it's pretty large by the time it gets out to Saturn.
Okay. Is it about the only planet?
I don't know.
Comment about the only planet. Oh well, that's okay. Oh, actually, I had a follow up to the question about contact. So what?
Oh, I meant the only planet. Oh, shoot! I call moons planets all the time. Because they are worlds unto themselves, and it's it seems kind of silly to differentiate between something that's orbiting another planet, something that's orbiting the sun. Really, if you're big and round, to me, you're a world, you're a planet. So my apologies for that, but I do that quite frequently because if I was the IAU, I'd probably call a lot more things planets than are actually planets according to their rules.
Well, speaking of that, I didn't get a chance to read it, but I saw something. I think it was today. About Pluto may have up to 10 moons. Did you see this?
No. I mean, we know it has 5 moons, but
right.
Yeah, I mean, they're discovering new things all the time, and yeah, I think there are a lot more planets than 8 in the solar system. I mean, you look at Titan; it's bigger than Mercury. It's got an atmosphere. It's got weather. If this thing wasn't orbiting Saturn, we'd definitely call it a planet. So it just happened to form around Saturn.
Right.
And there's good reasons for why it formed around Saturn, and it's not free floating. But still, if you didn't see Saturn in the background, you would call that thing a planet, I think.
Sure, yeah. And actually, if you're curious to know more about Pluto's moons, on this Friday, on CosmoQuest's weekly space hangout, they're going to talk about Pluto's moons. So if anybody out there listening is interested in that, check out the CosmoQuest weekly hangout on Friday, weekly space hangout on Friday. And just real quickly, I want to follow up again on the question about Contact the novel. How is the novel compared to the movie?
Yeah, the movie was pretty inspiring too. Because then you can see it in person. There were a few differences, obviously, between the two. But I think they did a good job in expressing. Although it's very funny to see the part about Arecibo, having actually lived at Arecibo, and know sort of where they are and how how unlikely some of the things that are happening would be. But
Sure, right. Well, I'll admit I haven't read the book, but I did see the movie. And though I am not a scientist, I'm an educator, the movie really inspired me to get involved in astronomy and interested in astronomy, and then eventually the planets kind of took over from there.
Right.
So it's a great story, I guess, no matter if it's the book or the movie.
Right, yeah.
So, all right. Well, it looks like maybe our questions have kind of slowed down from our viewers. So I want to thank you all for being a part of our hangout tonight. We're talking with Dr. Catherine Neish from National Guard Space Flight Center in Maryland. In just a minute, Catherine, I'm going to ask you for kind of any of your final comment you might have on what we've talked about this evening, or about anything you just want to say. And while she's thinking about that, I just want to let everybody who's online watching us tonight, let them know about tomorrow is the Planetary Society Hangout. So go to their event page for more information about that. And Friday is the weekly Space Hangout. And can learn about everything over on the CosmoQuest feed, about all these upcoming hangouts that are coming up. The audio for this show will be on the 365 Days of Astronomy podcast next Tuesday. And of course, the recording of this, as we saw on YouTube, should be up well, tonight probably, and we'll get this up as soon as we can for tonight. So thank you for coming and sharing. And I also remind everybody that the next MyMoon CosmoQuest Hangout will be, I believe, on April 2nd. And we'll be talking to Will Pomerantz from Virgin Galactic, some of that commercial space biz that's starting to take off. So we'll just I will stop with that horrible pun for the evening, and we're gonna go back to Catherine and see what any final comments that she has for this evening for you all.
Well, I guess I'm drawn back to what we were talking about, the golden age of planetary exploration, and we've done a lot in the past, 10 years plus to explore the solar system, but there's still so much we don't know, and so I really hope that the country and the world sees space as a priority to help us explore, be explorers, be discoverers of new science and new worlds in our solar system and beyond. Because I think there's something innate in humanity to be curious and to want to search out new places. And so I hope we continue to fund those programs in the future.
Well, I would agree. So thank you, Catherine, and thank you everyone for joining us tonight. And we hope to see you again soon. Good night.
Good night. Bye.